Keeping track of nonces. In practical terms, the nonce is an up-to-date count of the number of confirmed transactions that have originated from an account. To find out what the nonce is, you can interrogate the blockchain, for example via the Web3 interface. Open a JavaScript console in Geth or your preferred Web3 interface on Robston testnet, then type web3.eth.getTransactionCount of the string 0x9e7.124f. The output is 40. Tip: the nonce is a zero-based counter, meaning the first transaction has nonce 0. In this example, we have a transaction count of 40, meaning nonces 0 through 39 have been seen. The next transaction's nonce will need to be 40. Your wallet will keep track of nonces for each address it manages. It's fairly simple to do that, as long as you are only originating transactions from a single point. Let's say you're writing your own wallet software or some other application that originates transactions. How do you track nonces? When you create a new transaction, you assign the next nonce in the sequence, but until it is confirmed, it will not count toward the getTransactionCount total. Warning: be careful when using the getTransactionCount function for counting pending transactions, because you might run into some problems if you send a few transactions in a row. Let's look at an example. First command: get pending transaction count of the address is 40. Second command: send transaction from the address. Third command: get pending transaction count of the address gives 41. Fourth command: send transaction from the address. Fifth command: get pending transaction count of the address is 41. Tip: if you're trying to recreate these code examples yourself in Geth's JavaScript console, you should use web3.tway instead of web3.utils.tway. This is because Geth uses an older version of the Web3 library. As you can see, the first transaction we sent increased the transaction count to 41, showing the pending transaction. But when we sent 3 more transactions in quick succession, the getTransactionCount call didn't count them. It only counted 1, even though you might expect there to be 3 pending in the mempool. If we wait a few seconds to allow for network communications to settle down, the getTransactionCount call will return the expected number. But in the interim, while there is more than 1 transaction pending, it might not help us. When you build an application that constructs transactions, it cannot rely on getTransactionCount for pending transactions. Only when the pending and confirmed counts are equal, all outstanding transactions are confirmed, can you trust the output of getTransactionCount to start your nonce counter. Thereafter, keep track of the nonce in your application until each transaction confirms. Parity's JSON RPC interface offers the parity_next_nonce function, which returns the next nonce that should be used in a transaction. The parity_next_nonce function counts nonces correctly, even if you construct several transactions in rapid succession without confirming them. Curl --data with the following JSON. Method: parity_next_nonce. Params: a list with 1 string 0x9e7.124f. ID 1 JSON RPC 2.0. -h content type application/JSON -x post localhost 8545. The result is JSON RPC 2.0 result 0x32 ID 1. Tip: Parity has a web console for accessing the JSON RPC interface, but here we are using a command line HTTP client to access it. Gaps in nonces, duplicate nonces, and confirmation. It is important to keep track of nonces if you are creating transactions programmatically, especially if you're doing so from multiple independent processes simultaneously. The Ethereum network processes transactions sequentially based on the nonce, That means that if you transmit a transaction with nonce 0 and then transmit a transaction with nonce 2, the second transaction will not be included in any blocks. It will be stored in the mempool while the Ethereum network waits for the missing nonce to appear. All nodes will assume that the missing nonce has simply been delayed and that the transaction with nonce 2 was received out of sequence. If you then transmit a transaction with a missing nonce 1, both transactions, nonces 1 and 2, will be processed and included if valid. Once you fill the gap, the network can mine the out-of-sequence transaction that it held in the mempool. What this means is that if you create several transactions in sequence, and one of them does not get officially included in any blocks, all the subsequent transactions will be stuck, waiting for the missing nonce. A transaction can create an inadvertent gap in the nonce sequence because it is invalid or has insufficient gas. To get things moving again, you have to transmit a valid transaction with a missing nonce. You should be equally mindful that once a transaction with the missing nonce is validated by the network, all the broadcast transactions with subsequent nonces will incrementally become valid. It is not possible to recall a transaction. If, on the other hand, you accidentally duplicate a nonce, for example by transmitting two transactions with the same nonce with different recipients or values, then one of them will be confirmed and one will be rejected. Which one is confirmed will be determined by the sequence in which they arrive at the first validating node that receives them. It will be fairly random. As you can see, keeping track of nonces is necessary. And if your application doesn't manage that process correctly, you will run into problems. Unfortunately, things get even more difficult if you're trying to do this concurrently, as we will see in the next section. Concurrency, transaction origination, and nonces. Concurrency is a complex aspect of computer science, and it crops up unexpectedly sometimes, especially in decentralized and distributed real-time systems like Ethereum. In simple terms, concurrency is when you have simultaneous computation by multiple independent systems. These can be in the same program, for example multi-threading, on the same CPU, multiprocessing, or on different computers, distributed systems. Ethereum, by definition, is a system that allows concurrency of operations, nodes, clients, dApps, but enforces a singleton state through consensus. Now imagine that you have multiple independent wallet applications that are generating transactions from the same address or addresses. One example of such a situation would be an exchange processing withdrawals from the exchange's hot wallet, a wallet whose keys are stored online, in contrast to a cold wallet, where the keys are never online. Ideally, you'd want to have more than one computer processing withdrawals, so that it doesn't become a bottleneck or a single point of failure. However, this quickly becomes problematic, as having more than one computer producing withdrawals will result in some thorny concurrency problems, not least of which is the selection of nonces. How do multiple computers generating, signing, and broadcasting transactions from the same hot wallet account coordinate? You could use a single computer to assign nonces on a first-come, first-served basis to computers signing transactions. However, this computer is now a single point of failure. Worse, if several nonces are assigned and one of them never gets used because of a failure in the computer processing the transaction with that nonce, all subsequent transactions get stuck. Another approach would be to generate the transactions, but not assign a nonce to them, and therefore leave them unsigned. Remember that the nonce is an integral part of the transaction data, and therefore needs to be included in the digital signature that authenticates the transaction. You could then queue them to a single node that signs them and also keeps track of nonces. Again though, this would be a choke point in the process. The signing and tracking of nonces is the part of your operation that is likely to become congested under load, whereas the generation of the unsigned transaction is the part you don't really need to parallelize. You would have some concurrency, but it would be lacking in a critical part of the process. In the end, these concurrency problems, on top of the difficulty of tracking account balances and transaction confirmations in independent processes, force most implementations toward avoiding concurrency and creating bottlenecks such as a single process handling all withdrawal transactions in an exchange, or setting up multiple hot wallets that can work completely independently for withdrawals and only need to be intermittently rebalanced.